Hello, ladies and gentlemen. It's evening here, and I'm going to cover section 4.4 today, which is about the expectation of a function of a random variable. So this is actually an important section, and it introduces also a way of constructing new random variables from old ones. Okay, so 4.4, the expectation of a function of a random variable. So what does this mean? So we have x, a random variable, on our discrete sample space. Discrete means that S is either a finite set or it's a countably infinite set. Countable means it could be put in one-to-one correspondence with the natural numbers. And now I have G, any function from the real line to the real line. So then I can form the composition. So what I can do is, if you think of a function as inputs and outputs, I can do x first, and then I can do g afterwards to get a new random variable. And this is a new random variable. And what is it? It's denote it by g applied to x. Okay, and the main question is, what is its expectation? How do we compute it? Okay, so that's the main question, and we're going to answer that completely today. But before I do that, I'd like to do an example. So let me erase the screen. So here's an example. Let's consider a dice roll, a fair die roll, not dice, but die. A six-sided die. So S is 1, 2, 3, 4, 5, 6. And let G be the function G of x equals x squared. So what is G, and what is x? X is the value of a die roll. So that's our measurement. So what is G of x? Well, G of x, that's a function from S to R, and it's going to send a number I between 1 and 6. It's going to send it to I squared, clearly. Okay. So now the question is what is the actual, let's call this new random variable then y, and what is the probability? So what are the values of y? Well, y takes on values which are given by the squares of the first 6 non-negative integers, positive integers. So what is the probability that y is equal to a value x? Well, that's easy to check. It's going to be 0 if x is not equal to 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. And it's going to be 1/6 if x is any one of 1, 4, 9, 16, 25, or 36. So this is going to be the PMF of the random variable y. So I'm going to denote the PMF as P sub y. So it's P sub y of x. So what is the expectation of y? What's that given by? That's E of y. That's going to be the sum of the values of the x's multiplied by the probability of the x's. So that's 1 plus 4 plus 9 plus 16 plus 25 plus 36 over 6. So that will give you, if you add it up, 91 over 6. So that's the answer in that case. All right. So the next thing is to formulate the main result of this section, and that's coming now. So so here's a proposition. It's called proposition 4.1, and the situation is as above. X is a random variable on a discrete sample space, and G is a function from R to R, and we want to compute the expected value of G of X. Okay, so what is the expected value of G of X? Well, it's a sum, and it's of the form G of X times P of X where X ranges over the values of X. In other words, another way to formulate this is let's call the image of X the set of all X in the real numbers such that P of X, which is of course the probability that X equals X by definition, is not zero. So that's called the image of X. And so what I mean here is that we're taking the sum over the X in the image of the random variable X of G of X times P of X. Okay. So that's the answer to the proposition, and I'm going to give you a proof. Okay, so let me start on a proof. Okay, so let me clear the screen. Okay, so here's a proof of the proposition 4.1. Okay, so let's like assume, let's write the image of X as a set, X1, X2, X3, and so on. Okay, so now what is the expected value of G of X by definition? Well, it's, by definition, it's given by a sum, okay, and it's going to be, let me back up a bit. I'm sorry. I'm going to take this away. Let's consider the sum. So let's compute the sum of G of Xi times P of Xi over I. So that's what we want to show as the expected value of the random variable G of X. So then let's let the set y1, y2, y3, etc. equal the set of all the values G of X sub I. So it's going to be G of X1, G of X2, and so on. Okay, so then let's consider what we get. So then summation over I, G of Xi times P of Xi, what is that? Well, it's the same thing as the sum of the following, it's the following expression. I'm going to write it as a double sum. So I'm going to take G of Xi times P of Xi, but I'm only going to look at those G of Xi's which are given by some value Yj that appears in this set. Okay, so g of xi, notice that g of xi and g of some other g of xj could have the same value, g of xk could have the same value yj. And then if we sum up over j, we get everything, we get this sum here. Okay, so we have this double sum, and now I want to rewrite this double sum. So what is this? Well, this is the same thing as the sum over j, the sum over g of xi equals yj, as before, of, well, what is g of xi? G of xi is yj times p of xi. Okay, so that's what you get there. Let me clean this up, sorry. Okay, so right. So now what I can do is move the yj through the summation sign. So that's the sum over j yj times the sum over g of xi equals yj p of xi. Okay. Now, what is this expression here? This expression here is, oops, it's given by this, if you think about what that is, that's precisely the same thing as the probability that g of x is equal to yj. See, the probability that g of x is yj is the sum of these probabilities here by definition. Okay, but this is exactly the same thing as this expression here. Let me draw an arrow over here. This expression here is the same as the sum over j yj. What is this expression in the that I'm circling? That's exactly the same thing as the probability mass function. Oops. The probability mass function of the random variable g of x applied to yj. So, and that's by definition what the expected value of g of x is. Okay, so that's a sketch of the argument. The proof is over, and if you didn't understand it, it's okay. It's not the end of the world. Okay, so so what I want to do next is consider just a special case of this this example, which is going to be used over and over in the course of this proposition. So this is a corollary that appears in the text. So so let a and b be any constants, and then we can form the random variable ax plus b. That's a new random variable. So what is it? Well, you have x going from x is a function from the sample space to the real numbers, and then we have another function which sends a point x to a times little x plus b. So that composition is a uppercase x plus b. So what is the expected value of that new guy? The claim is that this is the same thing as a times the expected value of x plus b. And I'm going to give you the proof of the corollary. So what is the expected value of ax plus b? Well, that's by the proposition that we just proved. That's the sum over x's of ax plus b times p of x. where x is ranging over the image of x. Okay, now we can break this sum up. This is the same as by breaking up the sum. This is A times the sum over x times P of x over the same set x's in the image, plus B times the sum P of x, where x is ranging over the image. Now the first term is by definition the expected value of x times A, and the second term is B times this number here is actually this expression here is equal to 1. So this is going to be B times 1, so it's AX plus B. That's what we wanted to get. Okay, I think that's enough for this very short lecture. We've actually covered all there is to be covered for now in this. There are just some examples given in the text, which I don't think I'm going to cover now. And so we're going to move on to 4.5 in my next lecture.